Hello everyone, and welcome to the Chapter 3 review. We're going to go through some problems here about functions, how they are graphed, how they are defined, and properties surrounding them. So let's go ahead and get started with number 1 here. Which of the following equations defines y as a function of x? Now we actually have two ways to think about this. We can think about whether or not each value of the domain of these relations maps to exactly one image in the range. So we can think about how the values of x are being inputted into the equation and what is their outputs. Or we can think about whether or not the graphs of these relations pass the vertical line test. If they do, then it's a function. So we'll actually go through both of these. Let's start first with A here, y equals 1 over x. So if I graph this, so in our TI-84, I'm going to hit the y equals button, and then I'm going to type 1 divided by the variable x, and hit zoom 6. Maybe I want to zoom in a little bit. Obviously, we have a vertical asymptote right at the value x equals 0, because at x equals 0, my function or my equation would look something like y equals 1 over 0, and that's a big no-no. So I already know that I've got a vertical asymptote happening basically at the y-axis here. But if I were to try and pass a vertical line through any other value of x, it's only going to hit the graph once. So y equals 1 over x, yes, passes the vertical line test. I already know that x equaling 0 is not an okay value in the domain, right? The domain here we would write as all things or all values x, such that x basically cannot be 0, but x is an element of the real numbers. So my domain is good. Every value that I'm going to plug in for x, I'm going to get one unique y value out of that. X cannot be 0, passes the vertical line test. So A, yes, that is a function. All right, now let's look at B. Again, thinking about this in two ways. Graph it, see if it passes the vertical line test, or think about the values in the domain that are mapping to values in the range. If an x value maps to more than one y value, so if I have a picture kind of like this, where these are values in the domain, and these are values in the range, if a value here maps to more than one value over here, if one value in the domain maps to more than one y value, then we say that it is not a function. Not a function. To be a function, every value in the domain has to map to exactly one value in the range. Every x value has to have one and only one y value. So one way to do this is, again, graph it, explicitly express the function in terms of x, and then see what happens here. So as it stands right now in B, x equals y squared, this function is not written explicitly, meaning that it's y equals something. Y is defined in terms of the value x. So to do that, first I want to just solve for y. So y squared, to get y by itself, I'm going to take plus and minus the square root of both sides. So y, written explicitly as a function just solely in terms of x, we've got y equals plus and minus the square root of x. Now, here's how you would graph that on the calculator. I don't have a plus and minus button, so to do this, I really want to express that using y sub 1 and y sub 2. So in other words, I'm going to type the square root of x positively in y sub 1, and in y sub 2, I'm going to write the negative square root of x in y sub 2. So I get the entire graph. I get plus the square root and minus the square root. And we're going to hit zoom 6 to see that. All right, so the graph of plus and minus the square root of x clearly does not pass the vertical line test, right? If I try and put a vertical line at like x equals 4, I'm going to hit it at the top, I'm going to hit it at the bottom. Does not pass the vertical line test, so B, no, that is not a function. Another way to think about this is, pick a value in the domain. Pick a value in the domain of this function. So for instance, if I let x be 25, well, plus and minus the square root of 25 is going to give me values like 5 and negative 5, right? Because 5 squared is going to be 25. Negative 5 squared is also going to be 25. So here I have an instance where one specific value in the domain, like 25, maps to two different values, 5 and negative 5, in the range. Whenever that happens, I know that I do not have a function. So B, no, not a function. All right, let's move on to number 2. Determine whether the graph below is that of a function by using the vertical line test. If it is, use the graph to find its domain and range, the intercepts, if any, and symmetry with respect to the x-axis, the y-axis, or symmetry with respect to the origin. Okay, well, if I were to just put on some vertical lines here, it's looking like no matter where those lines are, no matter where they are placed on the graph, it's only going to hit my picture once, right? It hits there, down here, right? We see at those, it's only passing through the graph of my function once. So yes, this is a function by using the vertical line test. Now can I figure out the domain and the range? The domain is essentially all of the x values that get used by the function. So all values of x that get used by the function. Well, that's going to range anywhere from negative pi to positive pi, and inclusive, because those dots were originally filled in. They were not open dots. They have, all of these x values have some kind of output associated with them. So the domain is from negative pi to pi inclusive, so I use the brackets. The range, maybe I'll switch colors here. The range is all of the y values that get hit. So at most, we're up here at 1, and at least we're down here at negative 1, and all values in between are getting hit somewhere on the graph here. So we're looking at values of y that are possible outputs for any of those domain values. So that's going to range anywhere from negative 1 to 1. Okay, so again, the domain, think what x values are used. For the range, think what y values does the graph actually hit. Okay, so that answers part A. Part B, intercepts, if any. So let's get rid of some stuff surrounding our graph here so we can see our picture a little bit better. Okay, so now I'm looking for intercepts. Well, that is where we are crossing the axes. So we're going to hit it here, we're going to hit it here, and we're going to hit it there. To define those points, I need x, y coordinates. So for the first point, x1, y1, we would call that negative pi, comma 0. For my second point, x2, y2, where I'm crossing the y-axis and the x-axis, incidentally, that's at the origin 0, 0. And my third point at which that happens, x sub 3, y sub 3, well, that looks like it's happening at pi, comma 0. There are 3 intercepts. Okay, now just by the graph, just inspecting this, I don't have a formula or an equation to go off of for this function, even though it looks like a trigonometric function. I need to figure out if there is any symmetry. Well, I'm going to have y-axis symmetry if it looks like I can fold the graph along the y-axis and get a copy or get a mirror image on the other side. Well, if I were to fold this graph, the mirror image from the left to the right would look like this. The mirror image from the right to the left would look like this. So no, I don't have y-axis symmetry. If I were trying to think of x-axis symmetry, that would mean that I could fold along the x-axis and get a mirror image. Well, from the bottom to the top, the mirror image should be here, and from the top to the bottom, the other image should be here, and that's not what I have. So I also do not have x-axis symmetry. The last thing I need to check is, do I have symmetry with respect to the origin? Now, what that means is if I were to kind of anchor a point of the graph right here, right at the origin, and allow the picture to like spin like a pinwheel 180 degrees. So in other words, you know, this whole picture is spinning around 180 degrees. Would I get the other picture? So imagine like a push pin or a brad that has the little metal tabs that stick through the paper and bend behind the paper. Imagine it's getting anchored just at that one point. And the picture itself is then rotating 180 degrees around that anchored point. I would, in fact, get this kind of a picture on the other side. So yes, it is symmetric with respect to the origin. Just graphically, I can see that happening. All right, number 3, practice finding intercepts on the calculator for the function y equals x squared minus 4. So I've got a quadratic equation. I'm going to go back into y equals and clear out the stuff that I have. And I'm going to type in this new equation, x squared minus 4, and we'll do a zoom 6 here. Okay, so there's my function here. I want to find the intercepts, meaning I want to find the roots of the equation. Now, to do that for the x-intercept, so the stuff that is crossing the x-axis, we want to first hit the second button, and then we hit the trace button. Second trace, you'll notice right above there the little word C-A-L-C, calc. I want to calculate zeros of this function. So I'm going to scroll down and hit the second option and hit enter. Okay, now you notice the calculator is asking us a question. What is the left bound of my first intercept, particularly the intercept on the x-axis? So what this is saying is, what is kind of the left side of the point you're trying to figure out? Well, maybe I'll zoom in here a little bit. Let me zoom in. Okay, now that I've zoomed in, I'm seeing 2 places where it's crossing the x-axis. And when I hit this second trace 0, the left bound, if I'm using my scroll arrow here to get left of that first intercept, watch that little black cursor move. If I just kind of hover above the x-axis, I'm definitely going to be left of that intercept. I'm going to hit enter there. So you see that little black arrow, right? It's definitely going to be left of that first intercept. Now, if I use my right arrow key and go a little bit below the x-axis, I will definitely be right of that intercept. So imagine like a vertical line that is coming down between those 2 black arrows, that it would definitely try and hit the intercept right in between them. Then the calculator will ask you to guess, okay, and I put my cursor about where I think that intercept is, and then it tells me, okay, that 0 is happening at -2, 0. So x-intercepts, the first one is at -2, 0. Okay, now let's move over and find the one that is right of the y-axis. So I'm going to get my cursor going, and then I'm going to hit second trace again. I'm looking for a 0, but this time it's on the other side of the parabola to the right of the y-axis. So it's over here. Now, to be left of this intercept, to be left of that intercept, that point where I'm crossing the x-axis, I would want my cursor, my left bound, to be actually a little bit below it. See how that arrow would make a left bound to that intercept? And then to be right of that intercept, I would actually be a little bit above the x-axis. So you see how these two black arrows make the boundaries around that x-intercept? Now my guess is my intercept is right about in there. And then the calculator tells me the other one is at 2, 0. Okay, now how do we get the y-intercept? Let's zoom back out. How do I get the y-intercept? The y-intercept looks like it's at the minimum, at like the bottommost point of my parabola. How do I get that one? Well, I can also ask the calculator for specific values of x. So here's a rough sketch of what my parabola looks like. I would have a y-intercept happening right about there. Well, I don't know the y-coordinate of that, how far down it is maybe, but I definitely know the x-coordinate of that y-intercept is going to happen at x equals 0. So instead of doing second trace and then hitting the second option, I'm just going to use that first one there and select value. I want to know what's happening at x equals 0. So I click 0 and then I hit enter. Well, hey, that's happening down at y equals -4. So the y-intercept here is happening at 0, -4. So if you need to write down some calculator directions here, here's how I went about it. To figure out my x-intercepts, where we're crossing the x-axis, I hit the second button, and then I hit the trace button. And then I hit the second option down, and maybe it's not the second option on your calculator, but the second option down for me was to find zeros, and that means the roots of the equation, the places where it's crossing the x-axis, and then I have to worry about doing my bounds. So from there, you move the cursor. I have no idea how to spell cursor. Move the cursor left and right to kind of set boundaries to bound the location of the intercepts. Okay. Now to do the y-intercept calculator directions, you're still doing second trace to get into that calculate menu, second trace. But to get the y-intercept, you're not going to use the 0 menu option. You're going to use the one that says just calculate a value for me, right? So I know the y, any place where it's crossing the y-axis, that's going to be a y-intercept. The x-coordinate of those points is always going to be 0. So from there, you're plugging in x equals 0 and asking it to pop out what is the y-coordinate at that point. So very easy calculator directions to figure out intercepts of a graph. All right, number 4, let's list the intervals on which this function is increasing. Okay, well, we read a graph pretty much the same way that we read a sentence in English. You want to read the graph left to right. So anytime the graph is dipping downwards as you're reading left to right, that's going to be an interval of decrease. Anytime it looks like it's moving like up a hill as you're reading it left to right, that's going to be a period of increase. So as we kind of trace this graph left to right, I'm dipping down. This is going to be an interval of decrease. And then I hit a point where I start to change directions. I start climbing back uphill. So what I have in purple here, that's going to be a period of increase. And then I hit like the crest of the hill and I start going back down again, period of decrease. I hit a valley and then I start climbing back up. There's another increase. I hit a peak, reading left to right. I come back down again, and then I hit a valley and I start climbing back up the hill. So it's looking like I have 3 different instances, 3 different intervals on which f is going to be increasing. And the intervals, we define them based on their x values. So what I have highlighted here, That's happening whenever x equals -9 through x equals -3. So we say the interval on which f is increasing, well, from -9 to -3, that's going to happen. Then it happens again when x is -1 through where x is 1. So from -1 to 1, we're increasing again. And then a third time from when x is 4 to when x is 6. All of those intervals collectively are intervals on which f is increasing. All right, last problem for this first part of our Chapter 3 review. Use the graph of the function f below to answer the questions. A, list the values of x at which f is a local maximum. What are these local maxima if they exist? Part C, list the values of x at which f has a local minimum, and then what are these local minimum if they exist? So first, let's think about local maximum. Where are there peaks at certain values of x? Well, this looks like it's going to be a maximum. This looks like it's going to be a maximum. So where exactly is that happening? Well, it's looking like that's happening at -4 and at 12. Okay, so we'll fill in part A first, the values of x at which f has a local minimum. Well, that will be at x equals -4 and at 12. So -4 and 12 are the x values at which that happens. It looks like they're the same vertical distance up, the same value of y. Yeah, both of them are hitting right at 16. So 16 and 16 are both local maxima for these two different x values. All right, part C lists the values of x at which f has a local minimum. Well, it's looking like it's got two minimum values, one here and one here. So the first one looks like it's happening at x equals -12. And the second one looks like it's at +4. So x equals +4 and -12. Those are going to be locations of minimums. And the values at which that's happening looks like this one is down at -16. -16 for the first one and -16 for the second one. Alrighty, so this is part 1 of our Chapter 3 review. If you have any questions about these types of concepts, please feel free to contact me and we can talk through some of them further. Try and be as familiar as possible with this y equals button in the calculator so you can graph and zoom in and then use that second trace button to figure out certain areas of the graph like the zeros, values. You could have also used them to find minimum and maximum. If you have the equation of the function, it's the same kind of left and right boundary to isolate those values. So let me know if you have any questions.